So good morning, folks. Last time we talked about Lab 3 math, and I gave you a recurrence formula that allows you to step u, I, j at time t, n forward to u, I, j, n plus 1. So the iterative solution of this then is a boundary value problem, because you know the drum boundaries don't move. And it's an initial value problem because you know the distribution of energy you're putting on from the drum strike at t equals 0. So you know u of 0 at all ij, and you know u0 on the boundary I equals 0 or n max, I max. And you know the distribution actually at all times n on j equals 0 and j max. So there's a set of boundary conditions that you know, and there's enough information in, actually the state is un minus 1 ij, and un have enough information to compute n plus 1 time step, because if you know two positions, you effectively know the velocity of the point in time over one time step. So the difference of these gives the velocity, and the value of n gives the position, and those are the two state variables for a second order system. And each node is a second order system. It is a mass connected by springs to other masses. So, do you want me to write out the recurrence relation again and talk about it or not? It's in the paper, it's in the notes, okay. So there's just a couple of details on that I need to talk about that are left. Then I want to start talking about some of the physical aspects of the FPGA, because you're going to have to parallelize this code, and the way you do it is going to be dependent upon the amount of memory there is, the number of multipliers that there are, the number of logic elements, the interconnects, a whole bunch of interrelated things that you want to optimize. So we have to talk about the physical structure. And once you do that, you have to say, okay, how in the world are you going to simulate the physical structure? And there's at least two ways, maybe three ways of doing that. So I wanted to talk about that a little bit, because you probably saw my Piazza note this morning saying that by the end of the first lab next week, I want you all to be able to demo a 100-node drum to the TAs. And you can export, and to make sure it sounds good, you can export the simulation waveform as an Excel spreadsheet, import it into MATLAB, and play it. So that still leaves some details to talk about in parallelization, but let's get started. So the details that are left on the is some numerical stuff. Mostly, how accurate do you actually need u to be to get a reasonable solution? And what I'm going to claim is that 18 bits in 1.17 format is probably good enough. 18 bits in 1.17 format happens to be very close to what the audio codec needs to operate. It expects 1.15 format, a sign bit and a fraction. And so all you have to do for the conversion is to truncate the lower 2 bits off of your calculation if you use 1.17, and you get a signal which is suitable for feeding into the audio codec. Is that good enough? Well, I played around in MATLAB for a while and tried various resolutions. It turns out it's fairly hard to force MATLAB to do fixed point. So I'm not sure this is exactly right, but it appears that if you do 7 bits, the effect is silence. You get no sound out at all. So if you do a 7-bit simulation of the drum, you get nothing out, and it's probably because there's not enough accuracy for the wave to actually propagate across the surface. If you do 10 bits of accuracy, and you know, if you multiply the number of decimal digits by 3.2, you get the number of binary digits, right? And why is that? Think about it. And so 10 bits of accuracy here is about 3 decimal digits. Then you get a short duration. It's way too short. The numerical damping is too high, in other words. The duration is short, and there's a spectrum shift of something like 10%, so the errors are quite large. If you go to 13 bits, the spectral shift is 2%. And if you go to 17 bits, I couldn't see any difference from floating point. So 17 bits is about enough. And that's what I would recommend. There's a very good reason for using 18 bits, and that is that the native hardware multipliers on this chip are 18 by 18 multipliers. And so they'll do an 18 by 18 full multiply at 350 megahertz. That's pretty darn fast. So you're going to evolve this equation according to the evolution equation that we talked about last time, carrying about 18 bits. You can carry more if you want. You get a better sound out if you carried 27 bits, which is the next obvious size for the multiplier, because it does a multiplier will do a 27 by 27 multiply. That halves the number of available multipliers, however. So I would say that most of you are going to use probably 117 format, a sign bit and a binary fraction. You could think of this as line out on through the audio port is plus minus 1 volt. Turns out if you set the gain to 1, line out is plus minus 1 volt. So what you're saying here is that you have 15 bit accuracy on a 1 volt signal. So is there any questions about the math from last time, or what the lab is about? Okay, well, let's talk a little bit. I want to talk just a little bit about how you're going to parallelize this, and then I want to talk about the physical material that's available on the FPGA, and then talk more about parallelization. Basic problem is that if you run this state machine at 50 megahertz, if you run a state machine at 50 megahertz, then you have about 1,000 states between audio samples, because the audio samples are at just under 50 kilohertz, 20 microseconds. So you have right around 1,000 time ticks. To get the biggest drum possible, you're going to want to fill that 1,000 ticks with calculations. If you do the most trivial parallelization, which is you have one node, and what you're simulating is one node plus the connections to the neighboring nodes, and then you just duplicate that n times across boundaries here. Cross boundaries. Then, because let's say that you build a state machine that uses one multiplier to step through 5 or 6 steps. You can actually do it in probably 2 states, but 5 or 6 steps, or even 10 steps, then 99% of the time those compute nodes are going to be sitting idle, waiting for the next audio sample. Oh, that brings up an interesting question. How do you detect that a new audio sample is necessary and therefore start a new calculation? Again, there's at least 2 ways. One is weeks ago now, 2 weeks ago, we talked about the audio FIFOs, that the audio interface as abstracted by Qsys looks like a FIFO. If the FIFO is empty, you need a new sample. So calculate a new sample. Another way to do it, which I actually think is a little easier, is that one of the signals that exists at the output level of the FPGA, so it's on an I/O pin, is called something like DAC left-right clock. And it turns out that DAC left-right clock toggles at the audio sample rate, because it's saying, give me the left signal, give me the right signal, give me the left signal, give me the right signal, which is a serial protocol you really don't want to know about. But the rising edge of this clock is a synchronization point for a new sample, for starting the calculation of a new sample. And on average, you're going to have to calculate a sample about 50,000 times a second. If you toggle off the FIFO, you might do a burst of them and then stop. But it's a little bit of implementation dependency I don't want to talk about right now. So what would you do to get more operations? Let's say you're going to build a state machine that uses closer to 1,000 cycles. How could you do that? Hypothesis? Crazy ideas? Well, if you put 4 nodes together in one state machine, if you put 4 nodes together in one state machine, you could calculate the 4 nodes and then emit the answers on 8 wires, and then tile these state machines across the surface. And each one of those state machines would use one multiplier, because you can serialize it across those 4. Use one multiplier. And therefore, now you're limited by the number of multipliers on the chip, which it turns out for our chip is 300. You're limited by the number of multipliers to 300, but now you're looking at 300 tiles rather than 300 nodes. All right, well, communication scales well in this case. Let's do a 4x4. We do a 4x4. Now we have to make 16 connections for 16 nodes. So the connections are actually scaling well as a function, as a percentage of the number of nodes. The number of connections is going down because you have the perimeter related to an area there. So going to more nodes in a tile is certainly a valid way of spreading the calculations out over more cycles. So in this case, you get 60. You'd be using something like 20% of the cycles between audio samples. And the downside is you have to be a little careful about how you output these wires when you read them and when you write them, because there's going to be a serial load of all these wires and a serial read of the wires. So you have to make sure that that's synchronized. So that's one way of parallelizing it. Any other ideas about how to parallelize it? This is assuming, oh yes. Well, let's now talk about some of the hardware, because one way of writing a big state machine like this, what if we did 100 nodes on here? Well, maybe we're going to start running out of registers because it takes storage. It takes 2 words of state for each node. Maybe we're going to run out of memory, so maybe we should build one node block update state machine per M10K block, which is a memory block. The memory block, it turns out, is, well, that's what we need to talk about, because the size of the memory block might determine how big a block of nodes you want to update with one state machine. And since you're using M10K blocks, you're not using up logic elements for storage. But there's another way of making memory, and that's called MLab blocks, which use a very dense version of register storage. And that's what we need to talk about now, is the trade-off between register storage, MLab storage, M10K block storage. You can't use off-chip storage because it's not fast enough. That single threads, right? Then you can't do any parallel calculation. And we have to talk about multipliers. So, what is on this thing? Well, the chip we're using is a Cyclone 5 CSEMA 5F31C6. C6. As near as I can tell from the data sheet, that means that it has about 85,000 advanced logic modules, ALMs. 10 ALMs, ALM times 10, is grouped into one logic, into one lab, logic something block. $10? Really? 10? Not 8? Not 16? That's base 10. All right, so there's 10 of the logic elements in a lab, and up to a quarter of the labs can be used to make MLab memory. But for more detail, a logic element can be 2 6-input gates, and these are lookup table driven, so it can be any arbitrary function of 6 inputs. How many functions of 6 inputs are there? This is a straight up computer science question. 2 to the 2 to the 6th. That's a lot of different functions. So you can have 2 6-input logic elements, a 2-bit adder, although in arithmetic mode, you can use lookup tables in parallel with the hard adder to make a 4-bit adder. A 4-bit register, and a ton of muxes to route around all this stuff. And there's a normal mode in which you use these 2 input gates as gates, and there's an arithmetic mode in which you use them as an extended adder. And mostly, you're not going to care about that because you're going to let the synthesizer figure out how to fit your random logic onto the chip. However, if you decide to use all registers for memory, you will run out of memory in about 85 kilobits. And that's not enough. It's only a couple of hundred nodes. So you can't just blindly use registers for memory in this lab. You did in the last lab because you only needed 4 state variables, something like that, plus a few constants. Trivial. Now you're looking at thousands of state variables potentially for this lab. Which brings me to memory. Chip has 446 M10K blocks. So one M10K block could do an 8K by 1 bit. Could be configured to be 8K by 1 bit. It can be configured to be 512 by 20 bit. Or it can be 256 by 32 bit, among many other choices. This is not all of them. But for 18-bit arithmetic, that's not a bad match. Well, that would mean a 256 drum nodes would fit into one M10K block. We have 400 blocks. If we could compute them all in real time, we could do 256 times 400, which is, I don't know, 80,000 nodes or something. So if you could use all of these memory blocks, oh yes, and an important thing is that each memory block can do 2 operations on every cycle. It can do a read and a write on every cycle if you configure it that way. So you can get a tremendous amount of I/O bandwidth by using separate M10K blocks. And you can store lots of state variable, way more than you can store using registers. So you're probably going to want to use M10K blocks. However, and this is a trade-off I don't know because this is the first chip we've used in this class that has MLab blocks. MLab blocks, there's 679 MLab blocks. Each of which can be 32 bits by 20 words. My guess is that the point of an MLab block would be a fast register set for a CPU. That looks like about the right size. Maybe 2 of those blocks would make a really nice register set for a RISC CPU. And maybe that's how you want to write this, is as a whole bunch of RISC CPUs, stripped down RISC CPUs. But let's see, if we, so that's 10 nodes per MLab block, so you could get about 7,000 nodes if you used all of MLab memory for node state storage. But there'd be a waste here because you probably don't need 32 bits of accuracy. Any questions on this? Next thing is, all right, how do I specify, if I just give an array, if I specify an array like this, we have a register of 7 down to 0 of memory, 0 to 512. Then I've asked 511. I've asked for 512 words of 8-bit memory. How do I specify whether I want that in registers, M10K blocks, or MLAB blocks? And again, there's about 3 ways of doing this. One is you use an alt memory. You use the mega manager. You use a mega function which specifies memory. I think it's called alt mem. And you can force that to be anything you want. ROM, RAM, 1-port, 2-port, preload with data, not preload with data, whatever you feel like. It gives you a lot of control. It's not pretty because it's not Verilog. It is in a syntax which is dependent upon the Qsys 2 compiler. Right? It's a specific function. So the alt functions are a little less obvious how to handle, but they give you exquisite control, and they generate simulation files. When you compile a Altera IP module, it gives you a .vo file. V for Verilog, O for who knows what. You know, Muhammad? Anybody know? That's, oh crap. Fine. So that's one way. So way number 1 is use a mega module, which is there's an IP list in the upper left corner of the Qsys 2 design area. You can get that. Number 2 is to structure your HDL so that the compiler can tell what you're talking about. And I linked up a few more links in Lab 3 because I thought that 1,000 pages wasn't enough reading. And so there's now links called using Cyclone 5 memory blocks, DSP blocks description, and arithmetic mega functions. HDL style manual has information on how to formulate Verilog to infer the memory that you want. So there's information here on inferring multipliers and DSP functions, inferring memory functions, and then more literature, general literature. So Verilog multiplier in VHDL and Verilog, inferring multiply accumulator. I don't think you need that. Don't think. Let's go down and look at some memory someplace here. Multiply adders, inferring memory functions. And here's all the things that you can infer. Single port with initial contents, simple dual port, true dual port, single port ROM, and dual port ROM. Presumably a dual port ROM is 2 reads, not a read and a write. Then down in the body of this, it gives some information about things you have to avoid. M10K blocks have no reset line. You can't reset the whole block at once. There is no control to do that. Therefore, you cannot ask for a reset on an array. If you do, it will infer logic elements as registers rather than M10K blocks. So you have to avoid that. So it might be worthwhile reading the style manual on this because there's some other limitations. And there's some bad examples. Controlling RAM inference. So here we have Verilog HDL single clock, simple dual port synchronous RAM with old data read during write behavior. If you build a RAM, there's the RAM you're building, and you access it this way, Qsys will infer M10K blocks, and you can simulate this directly, of course, because it's just Verilog. But when Qsys looks at this, it'll say, aha, I recognize this pattern. That guy wants M10K. And Qsys will automatically stitch together M10K blocks if you ask for more memory than will fit in one. It'll just keep stitching them together until the memory is big enough, or until you run out of M10K blocks. So method number 2 is HDL style. Method number 3 is the weirdest syntax. At least I think it's strange. RAM style synthesis parameter. Maybe somebody should do a Gangnam style parody. So you can say, I like this format slightly better. You say reg my RAM, and then you say /*. So in Verilog, it's a comment. The Qsys synthesizer says, first word is synthesis. This is a command to me. And says, oh, RAM style equals M512 /*. Notice that it must come before the semicolon. If it's after the semicolon, it's just a comment. That's horrible. But it works. And you can't use M12K because those blocks don't exist on your chip. But you can use M9K, you can use N10, it's not on this list, M10K, MLab, and if you use MLab, it'll infer MLab. So you can force inference through a synthesis directive, which will be ignored during simulation. Any questions on this? There's too many possible ways to do it. Choose one, stick with it. What I've done in the past is just use HDL style. I think it's slightly cleaner than putting synthesis directives in. I've used the HDL style method, which also works for multipliers. And an example of this you've already used is my signed multiply module, straight Verilog, but it synthesizes, if you look at the compilation report, it's synthesized as a DSP module. So it's synthesized as a hard multiplier. Did anybody actually look at that in lab 2? No, of course not. But you're going to have to start looking at that, the compilation use report, intensively for lab 3, because you're going to run out of stuff. And it'll tell you when you run out, when it gets to 105%, it is not going to compile. Question, okay, memory. So DSP, multipliers. The DSP blocks do all kinds of stuff. There's 150 blocks. Because each block can do 2 18 by 19 multiplies. 18 by 19. can do two 18 by 19 multiplies, you have 300 18-bit multipliers. The reason for this is slightly obscure, but not too obscure. Most finite impulse response filters are symmetric if they are linear phase, right? If you want linear phase, they have to be symmetric, I believe. And that means that there are always two samples that have to be multiplied by the same coefficient in an FIR. So if you add them before you do the multiply, you get 19 bits. And then the coefficient is 18 bits. And so this halves the number of multipliers that are necessary for implementing FIR filters. That's cute. Not necessary to know for this particular lab, but cute. There are mega modules. In this case, I wrote them down, LPM mult. Straightforward. And then another one, alt mult, MULT, complex. Complex. And the alt here stands for Altera, not like alt-right. Right? So it's Altera multiply complex, and you're going to need that for lab 4. Or you might be able to use it for lab 4. Again, there is an HDL style option, which is explained in the HDL style manual. I strongly recommend you use that for bedtime reading this week. You can read a couple of pages, it'll put you right to sleep. And there's also synthesis directives. There's the mult style synthesis parameter. Which has an even odder syntax in that you specify the output wire to be a mult style logic, or you do this crazy thing times mult style equals DSP B. So you inline the style with the operator. I don't know what happens when you synthesize parentheses asterisk. Does anybody know? Does it ignore it? Does it go berserk? I don't know. Haven't tried that. So again, there's a synthesis directive. There's a synthesis directive for multipliers. In fact, there's a ton of directives. So I listed them all here. Most of them are of marginal usefulness. Though there is one other one I've used a lot, and that's RAM init file. You can specify that you want a specific memory image file associated with a specific memory block. So if you're doing a ROM, that's how you build a ROM, is to specify the memory image and then load it at FPGA program time. You could do that with a RAM also, but I would not use that for the initial conditions of the DROM, because when you press reset, those are not reloaded. They're only loaded at FPGA program time. So unless you have enough memory to store that someplace else and load it in over again, I would not do that. Now there are ways of doing that. You could load it into a memory image file. In your initialization code, you copy it off to SD-RAM, and then every time you need it, you copy it back into RAM. But But you're going to have to do a considerable amount of thinking. This is before you code, about how you're going to balance compute time, 1,000 cycles, compute logic, which is limited, in DSP particularly in logic elements, and storage for state variables. And all this has to be balanced against how much you like to sleep. There's the more you parallelize, the longer it's going to take to debug. So you have to do a balance of reasonable number of nodes and effort. I lowered the number of required nodes. I made the lab easier. I lowered it from 20 by 20 to 16 by 16 for one reason. And that is that with the number of 18 by 18 multipliers being 300, a 16 by 16 fits on the chip with trivial parallelization. So that means that you can do the minimum, get through the lab with only doing the most trivial parallelization, which is one compute per node. You build a node, you duplicate it 256 times, it'll work. There'll be a grade penalty for it, but you'll be done. So what's the grade penalty going to be? Usually we reserve between 6 and 8 points for number of nodes, scaled to the highest number in the class. And last year, as I think I said, the range was so great we had to take the log of the number of nodes and use that as the points. So you can get done, you can get a decent grade by going with the minimum, but if you have the cycles, do more parallelization. And I will talk next time about the best way I have seen to parallelize this. Because I want to give everybody, I'm not trying to hide anything. The best way I've seen to parallelize, I'm going to give you a teaser now. There's not enough time to do it right now. The best way I've seen to parallelize this was invented by a student, Skylar Schneider, who decided that if you had memory blocks representing each column of the drum, you could spew these out of the memory, and you only needed 2 intermediate registers to store the state while you were doing the drum update. And the number of columns you could therefore produce was determined by the number of memory blocks or multipliers, whichever was smaller, because you need one multiplier per column. The communication this way is free because you can do that in parallel through the interconnect. The communication in here has to be muxed a little bit, and I'll talk about that next time. But basically, you're then saying, we're going to do one column in 1,000 cycles. So if there's 100 nodes, that uses all of the cycles. 100 nodes will fit in one M10K block. In fact, twice that much will fit in one M10K block. So maybe you should do 2 columns per M10. So I'll talk about this in some detail next time. You can try and fill in the details. Like I say, there's a couple of boundary conditions that have to be met. So there's some multiplexers that have to say nearest neighbors are either boundary conditions or they are other cells. But that's a detail I'll talk about. There's another topic I need to talk about, and that is we're making copies of stuff. That's error prone, and so you're going to want to use a generate statement, which is a Verilog construct that generates Verilog. So I'll talk about that a little bit next time too. So think about parallelization. Think about all these resources. You've got a ton of multipliers. What would happen if you did a lightweight processor and an assembly language with 3 instructions? Would that do it? Maybe 5 instructions. It doesn't have to be Turing complete even. It just has to solve that equation. Or do you want to write state machines? Or what? Or do you want to try and do it on the HPS? I don't think you're going to get the throughput on the HPS that you can get off the FPGA. We also need to talk a little bit more about simulation, because probably you're going to want to simulate, after you get the solver running, you simulate the solver first. But then you're going to have to simulate the audio core state machine, which, like the VGA state machine, is required to do, it does a dance with the audio core module on through Qsys. But the audio core state machine has more states because you have to handle a FIFO, a dual FIFO, left channel, right channel, and you have to handle a data input to that FIFO. So there's more like 10 or 12 states rather than like 3 or 4 states. So you may want to end up simulating that, although in this case I've written that state machine almost exactly the way you're going to use it. So if we go down here to the Avalon Busmaster stuff, one of the last examples on here is audio output Busmaster, which is virtually what you're going to have to build, but with a different solver. Get some reading done. Start thinking about how you're going to parallelize this. There's lots of different options. Are you going to do clumps? Are you going to do columns? I relaxed the aspect ratio requirement. I said last time it had to be square. I'm going to relax it slightly so you can make long, thin. So the minimum aspect, the maximum aspect ratio is 4:1. You can have a drum which is 4 times as wide as it is long, but it has to be so it's between 4:1 and 1:1, which is square. Any questions? So the next 2 labs, this lab and the next one, the emphasis is on parallel computing. This is fine-grained uniform calculation. Every node calculates the same thing at the same time. You could have one state clock running all of the nodes because all of the states are exactly lockstepped if you did a fully parallel situation. The next lab will we'll have to have asynchronous state machines that are somewhat heavier because I'm going to be asking you to implement a complex arithmetic pipeline. And then multiple copies of that pipeline to feed the VGA display. Well, I'll see some of you in the lab this afternoon. Stop by if you have any questions. If you want to talk about hallucinate strategies for parallelization or anything else.